Okay, so we will be starting off with the fifth module today, right? Which is IC applications. So, so here in this IC applications, basically there are about three parts, right? So the first one will be 555 timer, and the second one is phase lock loop, and the third part is going to be DAC and ADC, right? So we are going to start off with the first part, which is 555 timer. Okay, so I think all of you are very much aware of what's a 555 timer, right? So you would have used it in your laboratories and for many experiments, right? So have you used them? Do you recall a 555 timer? Yes, no? Yeah. Okay. So, so this 555, just we will get into some of the basics of it. So this 555 timer, is it was actually designed in 1971, okay, by Hans Kamenzind. Okay, so that's the name of the scientist, and he was able to design it. Okay, and he was connected with Signetics Corporation. So this 555 timer is a highly stable circuit which is used to generate some kind of time delays, right? So if you have certain circuits, right, and you want to, you want to generate some time delays, then this is possible. Now, why do we need a time delay? As I've mentioned in my previous lectures, right, few systems will be very fast, but then few interfaced systems will be slow. For example, if you can compare the internal memory and the external memory, right, internal memory will be faster in operation compared to the external memory, right? So this is, this happens even with respect to circuit. So when we try to interface few devices, right, so those devices can be slow. So in order to make sure that the information is passed in properly, we use some delay so that the information is buffered and there is no any loss of information, right? Okay, so a single 555 timer can provide time delay which is ranging from few microseconds to hours. So there can be a time delay of few microseconds, or probably we can even give time delay of few hours, right? So depending on what kind of application that I'm looking into. So it operates from a wide range of power supplies. So it has the range of 5 to 18 volts, right? Now, the next one that will be seen is the configuration, okay, the placement of pins. So pin number 1 is connected to ground, and pin 2 is the triggering input that we're going to give. 3 is the output. 4, we're going to give reset, and pin number 8 is VCC, right? And pin number 9, pin number 6 is the threshold, okay? Then pin number 5 is control voltage, right? Okay. So based on what kind of connections that we need, for example, output, input, control, okay, and VCC, ground, so all these can be configured. So we will see few applications as to how we are going to use this 555 timer, right? So here we're seeing an internal structure, right? So basically it has about 4 components, 4 basic building blocks. Okay, so those building blocks are nothing but RS flip-flop, and then you have 2 comparators, right? So these are the comparators that you have, 1 and 2, right? Then you have reference voltage source, and then you have discharge transistor, right? So ground, trigger, output, reset. So I have put it up here so that it becomes easy for you to understand. Now we are using a transistor here, right? An NPN type of transistor, and internally it has resistors which is about 5 kilo ohms, right? So yeah, so now we will see how this comparators work, what is the function of comparator, and then flip-flop, I think you all know, right? The functionality of flip-flop, the SR flip-flop, right? Here you can see the truth table of the same, right? So we are looking at the internal structure, right? And what are the pins connected to them. Now, when a question is asked about functional diagram, right? So in that case, okay, you have to draw this diagram, okay? And this is the upper comparator UC, and this is the lower comparator LC, right? So there is something called threshold. You know, we have talked about threshold with respect to MOSFETs, with respect to transistors, right? So even here, with respect to 555 timers, we also have something called threshold. So this threshold, as we all know, right, is associated with a certain amount of voltage levels. So if this voltage levels are met, then it's going to start conducting, right? Or it's going to treat it as high. If not, then it's going to treat it as low. So depending on what kind of you know, or what level of thresholds that you're going to give, so accordingly it's going to change, right? So here we are looking at 2 by 3, okay, times of VCC. So if the threshold is greater than 2/3 of VCC, then I will consider it as logic 1. If my threshold is less than, okay, 2 by 3, 2/3 of VCC, then it's going to be a logic 0. It's going to be a low value, right? So at one of the terminals, right, I'm going to give this value, which is 2/3 of VCC. VCC can be, for example, 5 volts. So 2/3 of 5 volts, you can just multiply. And at the other end, we're going to give, threshold. So if threshold is greater, okay, then logic 1 is going to come. If threshold is less than this value, then logic 0 is going to come. So this is, acting like an comparator. So that is, these two comparators that you find here, right? The upper and the lower. And then you have standard resistors, which is about 5K, 3 resistors. And these two structures are the same, right? What I've done is I've just flipped it around, okay, so that it comes from left to right fashion, right? So here we have RS flip-flop, right? So we all know the truth table of RS flip-flop, right? Which is when R and S both are 0, then it will be in the previous state. When it is 0 and 1, then Q is enabled. When R is 1, okay, then Q becomes 0. When it is high, then it is a don't care state. So which means we have only these two states to be considered, which is 0, 1 and 1, 0, right? So it can be either greater than or it can be less than. So based on that, the value of R changes. Now for S, right? So if you can, imagine that, there is a small line here, right? So this is actually here, okay, and this is actually here, right? So these are the two comparators. Okay, now we can look at the next concept, right, which is the triggering. So in triggering, right, just a minute. So yeah, so in triggering, what we're going to do is, we are looking at activity. Okay, we are looking at activating something. So let us take this and connect it to S. Okay, so the output from here is going to be S. So if the trigger value is less than, okay, 1/3 of VCC, then S is going to go high. And if it's greater than 1/3 of VCC, then S is going to go 0. So based on this 1 0 1 0 combination and based on the property of an SR flip-flop, right? So we are just looking at ones and zeros coming here, and this gets into the RS flip-flop. And as usual, we have Q and Q bar. Okay, so this is the functional diagram. Okay, this is how your 555 timer works. So at one end you have the threshold, at the other end you have trigger, and you're setting references, okay, 2/3 and 1/3, right? So, and then discharge happens to this resistor here, right? And then we have an inverter, right? So inverter, and from here we connect to other devices, right? For example, PLLs or VCOs, anything for that matter, right? So we will look at it in our upcoming um, slides. Now, basically, there are two modes of operation, right? Number one is going to be the monostable vibrators, and second one is astable multivibrators. Okay, monostable multivibrators, monostable mode and astable mode. So when I say that these 555 timers are in monostable, then it means that it is trying to send only a single pulse when it is triggered. Okay, now that's important, right? Mono one, astable, which means not one but many is going to come, and it doesn't need a trigger. Okay, so astable multivibrators, it produces a square wave, right? At any point of time, it doesn't need an activating trigger to be done, right? But then in monostable, we need to trigger them, and it's going to give only a single pulse. Now let us look into the internal structure of this, right? So in the internal structure, right, we'll be able to understand what is exactly happening. So you can find this green structure here, right? So this is the battery, right? So it has a plus and the minus, right? So plus is nothing but the positive side of the battery, which is about 9 volts, and negative, okay, is 0 volts, right? And then those same resistors are there, the structures which we saw previously, remember? Yeah, these three resistors, right? 5K, 5K, 5K. So those three are again seen here, right? And then, we have a flip-flop here, okay, which actually is FF here, right? Is nothing but the flip-flop. So this works like a switch, zeros and ones, right? And what else? Yeah. The other important point here is, it is also called as one-shot multi-vibrator. The reason why we call it one-shot multi-vibrator is because, we need to trigger it. Okay. As soon as we trigger, there is a pulse that gets generated. Okay. If it's not triggered, then there's no pulse getting generated. But whereas in astable, what was happening, irrespective of triggering, it keeps on producing square waves. So that's the difference between monostable and astable. Now we are considering that this pin number 3, okay, pin number 3 is actually connected to 0 volts. So where is this pin number 3? We have it here, the output, right? So pin number 3, we are considering that it is connected to 0 volts. And so usually we take the output from it. Okay, so here we have the resistive divider. Okay, so one resistor here, the other resistor, then one resistor here, R4. So R1, R2, R3, R4, right? 4 resistors. And then, you have the capacitor C4 and C5. So again, 2 comparators here, right? And just like your UC and LC, comparator and down and lower comparator, and the same flip-flop, right? Okay. Now, what is this one-shot operation, right? So let us see the circuit. So as usual, the same 2 comparators are here. Okay. Then we have the resistors connected. Okay. And this is connected to a transistor, and one of the terminals, right, is connected to ground. So this will actually discharge whatever values are here. Okay, whatever values comes out from the RS flip-flop. Remember, it has Q and Q bar. So whatever values are there, that is actually going to drive the transistor here, because that's the base, right? That's the base. And after this, we're going to connect to the inverter, and we're going to get a final output pulse. So how is that happening? We are giving a trigger input of 1/3 for 1/3 of VCC. Now, what is this 1/3 of VCC? This was triggering and this was threshold, isn't it? Let's go back. Yeah. So this was threshold here, the upper one, and the lower one is trigger, right? For trigger, we were using 1/3. For threshold, we were using 2/3. So the same thing we are using here. So 1/3 is used for trigger, and it's just like a pulse that we give here. So as soon as this pulse is given, okay, it is set. One is there. Okay, if one is there, then immediately you can get the output pulse. If in case the reverse happens, then immediately this transistor is not driven. Okay, why is it not driven? Because the base is connected to the transistor, right? So ultimately, if there is nothing given to the base, then it means that we are not having any kind of uh, driving capabilities of this transistor. Okay. So the input trigger resets the flip-flop. So whenever we have the trigger given here, okay, the trigger given here through the terminal, right, what will happen? It will actually set means Q is going to be 1, and then C charges until the comparator trips and sets the flip-flop. So it will automatically charge the capacitor, and we are going to have an output pulse. Fine. Now we're going to look at it in the form of a block diagram, right? 2 is where we're going to give this 1/3 of VCC, right? And 7 and 6 both are shorted and given to capacitor, and this resistor gets connected to the ground via capacitor C. Okay. Now what is going to happen is just have a look at the waveform here towards the right hand side. So you have a trigger signal here. So this trigger signal is where we are actually giving here. I've put this arrow marks, right? So this trigger signal is given here. So this is to the lower comparator. So as soon as this trigger signal is given, the capacitor will start charging from the lower value to a higher value. So as this capacitor starts charging, you can see that the output pulse, I am getting a high wave. Okay. As soon as the capacitor starts discharging, the output pulse is going to go low. So the external component, okay, this external component, so this is the trigger. So I am considering this as an external, because I'm not depending wholly on my VCC and ground, but then I'm depending on the trigger here, right? So because of that trigger, what is happening? I am getting different type of waveform. So based on the time period, the duty cycle of this trigger, right, I can make sure that how much width my output pulse is going to be, right? So this is nothing but T, which is 1.1 times of RC. Now RC is nothing but a time constant, and you can call this as tau. Okay, resistance and capacitance value, and this is T is nothing but 1.1 times of RC. Okay, next we'll be looking at astable multivibrator. So in astable multivibrator, right, here also we have 555 timer connected, we have VCC, and then 2 resistors RA/RB. Now the equations are going to change here. Okay, so this astable, as we know, it doesn't require any kind of triggering, right? It can operate on its own, right? So that is one good thing. It doesn't need any external triggering. So hence it is also called as free running multivibrator. So astable multivibrators are also called as free running multivibrator, and monostable is also called as one-shot multivibrator, right? One-shot multivibrator, because it heavily depends on the triggering input, this triggering input, right? Okay, so astable does not require any trigger, as I mentioned previously, right, to change the output, and the period for the low and high can be calculated based on what is going to be the values of resistors and capacitors. I told you, remember the time constant, we looked at time constant here previously, right? So RC, which is nothing but also referred to as tau, right? So So that's the time constant values of R and C. So I can change if this pulse is going to be too wide or it's going to be too narrow. Now, how is it going to impact? It's going to impact because if it's wide for a long time, it means that, you know, if it's in the on state and for a long time, the width is there, okay, which means if the width is high, so which means we are giving more potential, right? It's on for a long time. So which means it can control the speed of, say, motor, or probably speed of a DC motor, or, anything for that matter. Right? Okay, so here 8 and 4 are connected, okay, and it's connected to VCC and resistor RA, okay. And since we do not have to give any trigger here, so 2 is connected to the capacitor, and in fact 2 is connected to the ground via capacitor, right? And my output, as usual, I'm going to take from pin number 3, and that is going to be a square. And the value of this capacitor, right, is going to be 0.01 microfarad. Usually we will use the ceramic type of capacitor here. Okay. So the period for low and high can be calculated based on R and C value that is connected outside the timer. So outside, I can decide, or I can configure the values of R and C. Now, C charges through RA and RB. So you can see here we have RA and RB. So this capacitor is actually charging once the current passes through, right? It comes here, and then you have RA, and then you have RB, right? So as the supply comes in, this capacitor is getting charged. So it is happening through the combination of RA plus RB, right? And then it discharges. It discharges through RB. Okay, because RB is connected to ground via capacitor. Okay, so the internal structure here. Okay, so we are looking at 2 comparators. Okay, and 3 resistors here as usual, 5K, 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 and the RS flip flop. Okay, and transistor here, and RA, RB. Now this capacitor, as I was mentioning, is getting charged via RA and RB because it is connected to VCC, right? So VCC is here, so the potential comes in, gets into RA, RB, and finally the capacitor charges. Okay, so this is also called as free running or astable operation. This is because we do not need any kind of external trigger. Okay, it just keeps going on without any external stimulation. Okay. Now let us look at few equations, right? So these equations are important. It could be asked for your examinations, right? So if you have to explain about the astable operation. So TH, okay, which is nothing but the time period when it's high, okay, and the time period when it's low. So TH is 0.693 times of RA plus RB into C, and TL is equal to 0.693 times of RB into C, because the discharge is happening via RB and the charging is happening via RA and RB. Okay, the combination of both. Now the period total T, okay, is nothing but the on and off. Okay, so I have off here, I have on. So this gives me a complete cycle. So this complete thing becomes one period. Okay, so this period is equal to TH plus TL. Okay, so which means it's going to be 0.693 times of RA plus 2 times of RB, because I have 2 RBs here into C. Okay, so my frequency F is going to be 1 by T, okay, which is nothing but 1 by TH plus TL, because T is equal to TH plus TL, right? So kindly adjust, this T has come a little bottom, so F is equal to 1 by T. If you can make a quick note there, and this is 1 by TH plus TL, because T is a combination of TH plus TL. Okay, so if I have to do this, then 0.7, right, is approximately 0.7. So 1.44 divided by RA plus 2 times of RB into C. Okay, so how do I calculate the duty cycle? On period, divided by the total period. So here what is on period? TH is the on period, okay, divided by, please make note here as well, students. It is TH divided by TH plus TL. TH is the on period, TH plus L is nothing but the total time period. Okay, TH divided by TH plus TL. So that's the total time period. Okay, next, so the percentage, since I'm calculating the percentage, so it is into 100. So TH, the charging is, RA plus RB divided by RA plus 2 times of RB. So I'm taking this, right? TH plus TL. And that is going to be multiplied with 100. Now you can see here there are two levels. The lower level is 1/3 of VCC and the upper level is 2/3 of VCC, right? So you can find that in blue, right? This is charge, this capacitor is getting charged from the lower end to the higher end. And then from high, the charge gets dropped down via resistor RB, and then it charges again to its maximum value to RA plus RB. Now, where do we see all these capacitors getting charged and discharged? We're going to see this, practically in the batteries, right? Any battery connected device, right? We would see these kind of operations happening. Now, it depends. These days we have this fast charging technology, right? Where, just within a split 15-20 seconds, right? 15-20 minutes, your whole battery operated device is charged, right? So that's the level of research and development happening in the field of battery technology. And as I was mentioning, right, this is a very interesting concept where a lot of R&D, a lot of research and development is happening just to make sure that batteries do last long. I was going through an article where the battery technologies previously used to be just lithium ion, and then now they came into first it used to be this lead acid, right? Lead acid technology, where acid, literally there used to be acid in the battery. So this was a little dangerous, and then slowly they migrated from that to the ion concept, right? The recombination concepts of ion. So once that kicked in, we were able to see lithium ion batteries. And then now, they have migrated to lithium polymer batteries. And next, it's going to be a different technology where, it will last for many years. Just, it will take very less time to charge, but then the discharge time is going to be very high. So which means, from this point to this point is going to be fast, but then from here, from the highest point of the capacitor voltage to the lowest point is going to take a lot of time. So a lot of research happening in this field, right? So what are its applications? Schemic trigger can be one such thing, right? We have seen this schemic trigger in our practicals, right? Then PPM. PPM is nothing but pulse position, okay, modulation. Then PWM is pulse width modulation, and then linear ramp generator. So if questions are asked with regards to application, then you can mention these. And it's not just limited to those, right? We still have many other things with regards to 555 timers. So coming to the conclusion, right, I would like to say that this 555 timer can produce very accurate and stable time delays from few microseconds to very large amount of time, which is few hours, right? And it can be used with supply voltage, which is about 5 to 18 volts. And the timer can be used as monostable mode and astable mode. And it has various applications, which is waveform generator, missing pulse detector, okay, frequency divider, and pulse width modulator, that is PWM. Then a burglar alarm. You can you can use this for your mini project as well, right? If you want to do a small project based on this. and the FSK, frequency shift keying generators, right? You will be studying about this in your communication labs, right? How it is so important to have an FSK. Then ramp generator, okay, something which has an exponential wave that comes in the form of ramp. Then PPM, which is pulse position modulation, based on where the pulse is placed, okay, the modulation happens. Okay, so this was, with regards to your 555 timers. So the next section, that we'll be looking into is phased lock loops. Okay, so this phased lock loops are nothing but uh, it actually locks a certain amount, okay, of waveform, right? And we will see how important this is, and what exactly it does in getting the job done. So many times, we will see that this application, right? This phase lock loop, will actually help us in understanding why is it so important to have this. Okay, why is it so important to have this kind of phase getting locked at a particular time? So we are looking at phase lock loops, right? This is the second part of module 5, which involves the operation principles, okay, the block diagram, and what is a phase detector, what is a low pass filter. Of course, we have seen this low pass filter exclusively, and we will just be looking into it, just for a brief time, and then VCOs, voltage control oscillators, and stages of PLL operation, and then what are its applications. Okay, so the first question is, what is a PLL, right? So the full form is phase lock loop. Okay, it's a circuit which helps in synchronizing an output generated by an oscillator with reference or input signal in the frequency as well as in phase. So we are looking at synchronization here. Okay, so if I need to have a constant phase, okay, then I'm going to lock it. I think you would have heard of this autopilot mode, right? Many of these advanced vehicles do have this autopilot mode where, or probably you could have heard of autonomous driving, right? So whereby it takes the control and it starts driving automatically. So here we are not looking at having varied waveform, but then we are looking at locking the phase at a particular angle, and the output is going to be constant as possible, right? So that is what is called a phased lock loop. Now here you can see there's a phase here constant, and the one in pink, okay, you can probably consider it as a general sine wave, and then blue also is another sine wave. So there's a constant phase, okay, that exists between both, and I will call that as phi. Okay, so even though I change the value of the waveform, okay, the one in pink, right? See the one in pink, right? So here throughout it is constant, okay? And here you can see that the frequency is not matching, right? So here by the time it finishes one wave, the blue, by the time it finishes one, here you have two waveforms coming, right? So the frequency of the pink wave is increased, right? Now where does this come in? Okay, I give an input signal or a reference signal, and this input signal is passed on to PLL, okay, and from PLL we get a constant output voltage. Okay, now you tell me, is it important to have a constant output voltage, or it's fine to have these deviations in the output, which is good?
Constant outputs.
Yes, constant outputs are specifically needed. That's the reason, if you can recall about op amps, we were looking at negative feedbacks, right? So because of this negative feedback, we were able to have controlled oscillations so that it is constant. Fine. So here you have something called F naught, which is equal to F in and small changes in the phase. Okay. So there can be two values here. It can be 0 or it can be a constant value. So I can decide how much of variation is going to happen here when I'm going to lock the phase, right? So that's in my control. So these are the three important functional blocks. We can make note of it. Number one, phase detector. Number two, LPF. Number three, VCO. So these are the three main blocks. Okay. So I have not represented here. Yeah. In the next, I'll be representing. Yeah. So if a question is asked about PLL, right, or explain about PLL, so you can put this diagram. Okay, wherein it has the phase detector at the input side, and then as it passes through the low pass filter, then I have some amplifier, okay, which actually looks or takes care of the error. Now this error, as I told you, whenever we give a reference, just like how we saw in 555 timers, right? Whenever reference is given, it will check for the reference value and it will tell if it is proper or not. If it's not in that range, then it will say that this is the amount of error, and a feedback is given here, right? In the form of VCO, a feedback is given, and accordingly we can change, right? So VS and FS is at the source side, voltages and frequencies, and F naught and V naught is at the output side of VCO, which is output frequency and output voltage. Right. Now look at this waveform very clearly. Right. So we have two two bifurcations here. One is the locked phase and the other one is unlocked phase. So the input is in frequency and volts, of course, and then here you're finding the low pass filter output, okay, and here is the frequency. Fine. So in the unlocked phase, right, so you can see that it is just moving, but then when I get into the locked phase or capture phase, right, you can see the outputs actually becoming stable. So irrespective of the frequency and voltages, right, they are trying to be made as constant as possible, right? So this wave is actually redrawn here, right? So you can see, with this kind of oscillations, how do I calculate the value? It really becomes difficult for me, right? And I'm not interested also to look at this kind of outputs. So I will need some constant outputs, right? A constant waveform like how I'm seeing here, that makes our job easy, right? So this is the importance of PLL, phase lock loop. It tries to make sure that the phase and the voltages are locked at a particular angle, okay, so that there is no disturbance at all, right? Now what are some of the stages that happens, right? So there can be free running stage, and the second stage where it was constant is called capture stage. Now what is this free running stage? Let's get back to the previous slide. So here you can just see that these waves are going up and down, right? So this is called a free running phase, and the phase at which it becomes constant here, right, it's called a capture phase. Okay, so when no input is applied at the phase detector, so whenever there is no input at the phase detector, then due to VCO, the PLL works in free running stage. So what is this no input? There is no VCO here, right? The phase detector has no input. So in that case, it is looking at outputs which is not constant at all, right? It is looking at outputs which are varying. So once it gets into this capture mode, right, you can find that the waveform becomes constant. Okay. Fine. So these are the two phases here, right? Which is unlocked phase and locked phase. Right. And now in the next one, the output frequency of this stage is dependent on the free running frequency of VCO. So, there's no feedback happening. So because of which our outputs are varying up and down. Now, when I look into capture stage, right? So in this capture stage, the input frequency is applied at the phase detector. So you are finding some inputs that is given to the phase detector in the form of feedback. And this feedback is, given with the help of VCO. Okay. So due to the feedback, PLL tries to track the output with respect to input. So it is able to see, right? Oh, this is my output and I have to keep it in this stage, right? This is my input. It is just like, bringing something into track if it is going off track, right? So that's about it. And in this stage, I call it as capture stage. Right? Capture, it's just like, probably when you're taking a video, you have an option to capture an image, right? So even though the video is on, right, I'm able to take a snapshot of it, right? And the people or the objects don't move at that time, right? When you take a photo. So it's as good as a screenshot face, right? Then I have phase lock state, right? So due to this feedback mechanism, what is happening? The frequency comparison happens, okay? And it stops as soon as the output frequency becomes equal to input frequency. So it will try and wait till they match up the inputs and the outputs, right? Once they match up, right, you will be able to see that it is locked and it's going to be constant. Now you can see in the next slide, right, where the capture range we are talking to about, right, is F0 minus FC. So this is my lower end of the frequency, and F0 is, the center frequency. Remember, we were discussing about this F0 in filters, isn't it? So, and here we have F0 plus FC. Right? Okay. So this is the cutoff frequency. So this full thing here becomes my capture range. So the range of input frequencies around the VCO center frequency onto which the loop can lock when starting from the unlocked condition, right? So here it is unlocked, here it is in unlocked state, right? And slowly it starts becoming constant, right? And it gets into locked mode. So immediately you cannot find this output, right? So slowly, you can see that it starts becoming constant, and once it's in capture mode, right, it starts becoming stable, right? So this whole range where it starts becoming stable is called capture range. Now, what is the lock range? The lock range of input frequencies over which the loop remain in the lock condition once it has captured the input signal. Now, yeah, I was talking to you about this cruise control and automated driving. So in this cruise control, you have the option to actually control the speed. It can just go in a single speed. You don't have to use the throttle, right? You don't have to use anything else. You just need to press that cruise control, right? And once that is activated, the speed becomes constant. So you don't have to worry about any changes in speed. It remains the same whatsoever, right? So that's one application that you can think of, in the field of automobiles, right? Okay. So that's nothing but called the lock range, right? So that's the range of input frequencies over which the loop remain in the lock condition once it has captured the input signal, right? So that's the minimum frequency value, okay, F0 center frequency, and the maximum frequency F max. Okay. Now, what is this phase detector? Right? What does it involve, and how is it able to function in this fashion? Right? So phase detector is basically a comparator. So it will try to compare, and usually it is having an XOR gate. Now we all know what's an XOR gate, right? If the inputs are same, the output is going to be 0. And if the inputs are different, the outputs are going to be high, right? Which means 1. So phase detector is basically a comparator that compares the input frequency F in with the feedback frequency F out. So two types of frequencies here, and the comparison happening between these two frequencies. So comparing the input frequency and output frequency, it provides an error signal, right? So that is what you see here in the wave, in the block diagram, the error amplifier. So the errors are amplified and then a feedback is sent to rectify. Okay. Provides an error signal, which is basically a DC voltage. Fine. The loop is locked when these two signals are of the same frequencies, right? So it will try and adjust till the frequencies are same. Once it is same, the loop is locked and there's not going to be any changes. Our outputs are going to be as constant as a straight DC line. So basically it involves an XOR gate, as I mentioned. Now let us look in the form of equations, right? If alpha and beta are, two different signals, right? So alpha minus beta. So I'll be having a sine function here. Okay, so I'll be expanding sine A minus B, right? And this section here, okay, when I multiply them, sine alpha and cos beta, right? When I multiply them, I am going to get a factor here, which is sine alpha plus beta divided by 2. So this is nothing but the low pass filter, right? Low pass filter. So the one which we saw here, yeah, low pass filter. So from the phase detector, it gets into the low pass filter. So which means behind the screen, there are these equations that is working out with the phase difference, right? So you can think of, this diagram here. I have given two frequencies, F1, F2, right? I probably add them or minus them, right? I get certain values, and then these values are passed on to LPF, which is low pass filter, okay? And I'm going to get F1 minus F2. Now, what is this PLL, right? It's a phase detector. In RF applications we used for balanced mixer, right? And in the field of digital electronics, then it works as an XOR gate, okay? Frequency, phase frequency detector. If there's any change, right, we will be able to sense it. So I'll be showing some waveforms as well, right, in my upcoming classes, upcoming lecture slides, right? So you will be able to understand how this XOR gate is functional. Right. Now, this is an analog phase detector, which is switch type, right? I have an input signal, which is Vs, and an electronic switch, which turns on and off based on the values 1 and 0. And I get my outputs Vc. Now this drive, okay, this drive, which is actually from a VCO, which means, you can consider this as a feedback signal from a voltage control oscillator. Fine. What is the analysis here? A phase comparator is basically a multiplier which multiplies the input signal. Okay, that is nothing but Vs is equal to V. This is small Vs. Okay, Vs is equal to Vs into sine 2 pi Fs into T. So this is nothing but the source frequency by the VCO signal. So what is this VCO signal? V naught. Okay, you can see here V naught, which is equal to the output voltage V naught into sine 2 pi F naught T plus the phase difference phi, right? So you would have seen this in your DSP, digital signal processing. The same equations are used here, right? So the phase comparator output is going to be, the total output is going to be KVS into VSO, right? I'm just multiplying both the terms. So sine 2 pi FST, which is here, into, right, sine 2 pi f naught t plus phi. Okay, so what is this k here? It's a factor, it's a gain factor, or it's a constant. It is just like a knob. You can think of a knob. I can probably increase the knob or decrease the knob, right? Okay, so it's a comparator or an attenuation constant, and phi is the phase shift between input signal and the VCO output. So what is going to be the difference between the two signals is going to be phi. Remember, I showed you the one in blue, the sine wave, and the other one in pink, right? And between both of them, we had certain difference, right? So that was termed as phi. So that is the phase shift. Okay. So if I have to put them in the form of equations, right? So it's going to be, k into Vs, okay, V naught divided by 2, and I'm going to add a cosine function here, okay, and minus 5, okay, minus 5 plus 5. So I'm going to use my trigonometric functions here. So when it is in log phase, that's when Fs is equal to F naught, the source and the output frequencies are same. So this is going to be the final equation here, right? Which is cos minus phi minus of cos 2 pi to f naught t plus phi. So you don't have to derive this. You just have to know the final equation. Now let us concentrate on these waveforms here, right? What is the error voltage? Okay, what is the error voltage at 0, and what is the error voltage at positive side, and how is the VCO output, right? Okay, so I have a signal here, and this that you're seeing here, right, is across the phase shift phi. So when phi is 180, the error is actually occurring at the negative side. Okay, when it is 90, you can see that the error is both at the positive half and at the negative half. And when it is 0, it is only in the positive cycle, right? So yeah, so this is how the errors are actually mapped. Okay, and it will try and make this Fs equal to F naught, okay, based on the feedback uh, given to the phase detector via VCO. Okay, so at this point of time, right, when I have a low VCO output, right, so you can find that there is no error happening, right? There is no error, there is no any grade or shaded portion, right? So only when it is in high, okay, only when it is in high, we are seeing that, at different phases, at different phase shifts, right, it's going to actually show us the error, right? So it's a pulsed mode, it's a pulse, so we call it as a switch type 0 1 0 1, right? So this is in 0 mode, 1 0 1, and so on. So it's called an electronic switch. Now here, right, we'll be able to understand what is this XOR gate. So when it is in 0 phase shift, okay, when it's in 0 phase shift, you can find that the difference in this phase shift, okay, that's delta phi. You can just find, this kind of spikes only in the positive cycles, positive pulses of both V1 and V2. Now, as it changes, okay, when there's a slight shift in the voltage signals, you can see that the green one is shifted slightly towards the right, right? So in the 0, right, you find that they are aligned in the same line. But then when I go to 90-degree phase shift, right, the V2 is actually shifted a little towards the right, right? So you can see that at this point, wherever, it is high, okay, this portion is high here, so I'm having this high pulse, okay. So this is working like my XOR gate, right? So this is 1 0, so I'm getting 1. So when it is 1 1, I'm getting 0, right? So if you can probably draw a line, okay, you can actually understand how it is, right? So this is 1, okay, and let us have it here. Okay, so So you can find at this point what is happening. It is 1 1. So I am getting the value 0. And at this point, okay, it is 1 0. So I'm getting 1. Okay. So this is how you should actually analyze it. Okay. Right. So I hope you have understood this waveform. Now let us go to 180-degree phase shift. So in 180-degree, what is happening? You can see that it has fully moved to the negative side. So negative, or probably the off pulse of P1, right? But then in 0, they were aligned. Positive is positive here. Now, off state is also off state here, right? But then in 90, slightly, it's little in the on side and little in the off side, right? And then when I move to 180, here it's off and on and off. So it's a full shift. Okay. So meanwhile, you need to concentrate on this delta phi, right? So you can see that every time the pulse is high because it's 1 0. So I have 1, okay, 0 1. So always, I'm getting this high signal. Right. Now, if I have to, put this in the form of voltage and phase difference, if I have to map them in the form of graph, right? So this is how it would look. So towards my one of the axes, I've given voltages, which is V, which means the highest voltage. It can be even 5 volts or it can be 10 volts, and V by 2 is exactly half of it, right? And exactly at 180 degrees, right? 0, 90, 180, 270, 360. So what are all this? The phase differences. So here I've showed for 180. So again, if I move still further, right? So it's going to be 270. And then if this can actually come here, okay, then it becomes 360, right? So yeah. Now what's a low pass filter? We all know what's a low pass filter, right? It allows only the lower frequency signals, and the higher frequency signals are all blocked, right? So low pass filter is used to remove high frequency components and noise from the output of the phase detector, right? So lower frequencies are allowed and higher frequencies are nullified. Low pass filter provides a steady DC level voltage, which becomes the input for VCO. So let's get back to that diagram, which actually tells us about the connection that is between the phase detector and the low pass filter, right? Okay. So it provides a steady DC level voltage, which becomes the input of VCO. So two frequencies, the same thing I've, re-brought it here. Okay. Next, VCO. Right? VCO is nothing but voltage controlled oscillator. Right. So what is this voltage controlled oscillator? Okay. We see that in this oscillator, right? It generates frequency controlled by input voltage. So whatever is the input voltage, right? So based on that, the frequency is controlled. So at one end, it's going to be voltage, right? And at the other end, it's going to be the oscillation. So as the voltage changes, the oscillation also does change. Okay. So I am controlling the oscillation based on the voltages. So the DC level output of a low pass filter is applied as control signal to voltage controlled oscillator. So this DC level output, so the output that comes from the low pass filter, okay, is applied as control signal to the VCO. In fact, before VCO, we have another block which is called the error amplifier, right? So this VCO is adjusted till it becomes equal to the input frequency. So we have seen that once it becomes equal, that's when your phase detector gets the input and it starts becoming constant. Okay, So during this adjustment, PLL goes through 3 stages. Okay, that is free running, capture, phase lock. So free running, the waveform which I showed you, a complex waveform, and capture mode was the point where it started becoming constant, and phase lock is where it's always the same. So what are the applications involved, right? It can help in synchronization and demodulation circuits. Now synchronization, is it important, students? While passing information or in the field of communication, is synchronization important? Yes, no? Are synchronizations important when we communicate things?
Yes, sir.
How is it important?
Sir, if we don't synchronize, then there might be a lag in the way we speak
Very good. That is one good point. And
or disturbances.
very good. And there can be chances of data getting lost if in case there's no synchronization, right? So that's the important thing. And demodulation circuits, right? Clock recovery, if in case you want to have an extra pulse there. So because of the property of XOR gate, right, we can actually generate an extra pulse. Then noise and jitter reduction, frequency synthesizers, microprocessors. So in microprocessors exclusively, we'll be touching upon with the clock multiplier and clock distributor, just like the multiplier and divider that we saw, analog multiplier and divider, right, with the help of op-amp. So similarly here, that is again a part of the application. Okay. So next, we'll be seeing how this VCO works. Okay, so this VCO here that we are looking into, right? So it's an oscillator which produces oscillating signals or waveforms with variable frequency, right? So based on the voltage, I can control how the oscillations happen. So the frequency of this waveform is varied by varying the magnitude of input voltage, right? So control voltage is here, and I'll term it as VC, right? And the output frequency here I'm taking as F naught, right? So if we can plot both of them together, right? At one side the voltages and the other side the frequency, right? You can see that as the frequency increases, right, as the voltage increases, the frequency also does change. So there's a increased level of control that happens as the voltage is changed, right? Okay, so you can look at these diagrammatic representations, right? So in an oscillator and voltage controlled oscillator. So here, I'll have to use this R, C, and L, right? So in a voltage controlled oscillator, I just need a control voltage. It's connected to VCO, and it's going to be a stable output. But then here, DC voltage is given. This oscillator again has control. I have to design, the R's, C's, and L's, right? And after doing all of that, right, that's when I will get a stable output, right? So these are the types of voltage that we see. The two types of VCOs. One is harmonic oscillator, and the other one is relaxation oscillator. So harmonics will actually generate sine waves, right? Relaxation oscillators, they produce sawtooth or triangular form. So if I need a sawtooth waveform in my output, right? So I'll be using a relaxation oscillator. If not, then I'll be sticking with the harmonic oscillator. So we will just look into the schematic diagram, and then we'll be looking into few equations, that is the internal structure, and then the equations, right? So this was the configuration that I was talking to you about, the pin configuration. right? So it has dual inline package, right? So first is ground, and then 1, 2, then 3 is your square wave output, right? You have two comparators here, right? Schemic trigger, then you have current sources, right? Modulation input is given here, the timing resistor, timing capacitor, that is RC, right? R and C, and then VCC, right? So this is going to be your complete LM566 IC. So if a question is asked, draw a functional or pin configuration, then this is going to be your answer for it, right? So current sources, comparators, schemic trigger, and you can mention the timing capacitor and the timing resistor, right? So here we're going to get the triangular wave output. So based on what kind of VCO, if it's going to be a relaxation type, then it's going to be a square tooth. If it's a harmonic type, then it's going to be a sine, right? So the functional block now, right? This is the pin diagram, right? Just a skeleton view. But then if we get into the structure of it, right? The functional block, right? Here we will be able to see the um, gains A1, A2, A3. Okay, then capacitor C. Okay, then resistors A and B. Okay, then VCC. So these are different pins that they are connected to, right? At pin number 4, what you're going to get, at pin number 3, what you're going to get, right? So this is going to be a relaxed type of VCO, and this 3 is going to be the harmonic type of VCO, right? Or you can maybe convert it, right, and you can get a proper sine wave. Okay, so this is the internal structure, right? So now we will see some equations, right? We will break it up into still smaller pieces, and then we will look into the equations. So this capacitor is about 47 nanofarads, right? And this is also the IC LM566, right? And we have resistors R1, R2, okay? Capacitor C1, as I mentioned, 47 nano, and C2 is 1 nano. Right? So just see the waveforms here towards your right hand side. Output, you're going to get a triangular waveform at pin number 4, right? So this is about 0.5 times of VCC, half of VCC, right? And the quarter of VCC is going to be the low value, the lowest value, right? So that is 0.25 VCC. And the schemic trigger output, right? The highest point is going to be VCC, and the lowest point is going to be point or half of your VCC. So say if it's about 5 volts, then 2.5 is going to be the lowest point of schemic trigger output. And the same thing is actually employed here for output at pin number 3, right? So what is this pin number 3? Pin number 3 also you have an power amplifier, right? And an inverter, which is a power amplifier. So here, yeah, squared wave output. So this is a power amplifier, which means it can handle higher powers. Okay, it can handle higher levels of powers. Okay, now concentrate on the equations here, right? So in this equations, you are seeing that the capacitor charges from 0.25, right, quarter of VCC to half of VCC, and the change, okay, if I minus these two, then it's going to be about 0.25 only, right? So that's delta V. Now delta V by delta T, right, is nothing but I by CT. CT is the total capacitance value, okay, the time it takes. So so this delta V is 0.25, okay, times of VCC. I'm just bringing it down, delta T, which is equal to I by CT. So I will just take them across, right, cross multiply them, and just keep delta T at one side. Okay, so this is a conversion of a time, okay, the voltages levels to frequencies, right? So delta T is going to be this value based on my cross multiplication, and I, okay, I is going to be the current through is given by I is equal to VCC. This is our standard form. Okay, VCC minus VC, the voltage across capacitor, divided by RT, the total resistance. Then the total time period, okay, T is equal to 2 times of delta T, small change, right? Because it's 0.25 to 5, right? So 2 times of delta T here, is going to be this. So 2 times of delta T. So the frequency F is equal to 1 by T, right? So F naught is equal to, okay, 2 times of VCC minus VC, okay, that is here I, okay, 2 times divided by CT RT VCC. Okay, so just remember this equation here, F naught, and we will be using that further. So with no modulating signal input, right? So let us assume that there's no modulating input signal, and if the voltage at pin 5, okay, this is actually is biased to 7 by 8, okay, of VCC, then what is going to be the F naught? So F naught is equal to 2 into VCC minus 7 by 8 times of VC. So if it's not VC, but it's 7 by 8 times of VC, right? So that is going to come up here. CT, RT, VCC, anyway, just carry forward it. Okay. So, I want it in the form of 0.25. So I'm just bringing this, right? Then I have the factor, the gain factor, right? KV, we saw K previously, the gain factor, which is, change of small change in frequency divided by, small change in the voltage in the capacitor VC. So VC is nothing but, the modulating input which is required to generate, and this is the change in frequency or shift for VCO. Now, this small change, remember I showed you F naught minus FC, F naught plus FC, right? So minus FC came towards the left hand side, and plus FC was at the right hand side, extreme right hand side, right? So what are we looking at in these levels? So we are just looking at the change in frequencies with respect to FC, the cutoff frequency, and the center frequency F naught. Okay, so let us now assume that this F1 is the new frequency, and delta is of course the change. Then what is going to happen to BC? So delta F naught, F1 is the new frequency minus the center frequency. So F1 I'm going to retain here. So delta F naught minus delta F naught, okay, plus F naught is what is going to happen here, which is 2 times of VCC minus VC divided minus small change in VC divided by CT, RT, and VCC. That remains the same, right? So if I have to compare this fourth equation and first equation, right? So here the first equation is 2 times of VCC minus VC and CT. So if I have to compare both of them, right? So small change, is actually going to be 2 times of delta VC. Of course, the denominator is going to be the same. Okay. So yeah, so you can draw this diagram, put the circuit and the main equations, and what is delta with respect to voltage, what is delta with respect to frequency, you can explain. Now, what are going to be the applications of this? Electronic jamming equipments, right? One application is going to be jammer, where you don't get any signals, right, for your cell phone, and the production of electronic music, for production of different types of noise, right? So based on how much of voltages I give, my oscillations will change. So if my oscillations are changing, then the way the sound appears is also same, because sound or noise is also frequency, right? So a phase lock loop, The applications are going to be frequency synthesizers. It's used in communication circuits, function generators, tone generator, FM, right? In FM's frequency modulated systems. Then FSK's frequency shift keying, and for generating clocks, right? So why I'm able to generate clocks? Because I do have stable, constant values of waveforms, right? So it is as good as a clock, right? So PLLs can be used for generating clocks, right? So with this, we complete the phase lock loop, right? The second part of module 5. And in our upcoming lecture, right, we'll be looking into DACs and ADCs. So we have two more topics left, which is DAC using R2R ladder, that is digital to analog converter using R2R ladder. And the other one is ADC, which is analog to digital converter. Okay? So these two concepts we'll be studying in our upcoming class, right? So any doubts up till this point, students? No?